Okay, good morning, everybody. And welcome. I'm so glad so many of you are able to attend. I am going to take my mask off because I'm far from you and just for this introduction, so please bear with me. I'm really pleased that everybody could be here today. I think this is also virtual, so welcome to our virtual partners out there, and it's being recorded. If you had told me several decades ago that I would be here today as your dean introducing Candace, I would not have believed you. And it is absolutely my honor to be here today and do that. So congratulations to Candace on winning the Distinguished Achievement Award. Actually, she won it last year. We just weren't able to actually have an event until this year. So I'm really pleased that she can be here today to offer us some of her insights and reflection on what's going on scientifically in Narragansett Bay and perhaps some of the things that we can think about for the future. So this is the part where I get to tell you a smidge of just her life story, which I'm sure is a lot more amazing than I have time to talk about today. Raised in inland Connecticut, Dr. Oviatt didn't know much about the ocean, but her natural curiosity drove her to learn a science called oceanography. She enrolled at the University of Rhode Island Graduate School of Oceanography in 1961, the year that it was established, and she earned her PhD in 1967, the first woman to do so. There are not many people who know more about Narragansett Bay than Dr. Candace Oviatt. Beginning as a research associate, Candace was promoted to full tenured faculty at GSO in 1980, one of the first women to attain that position. Now I'm just going to pause here for a second and say I spoke to many people in Candace's history who know her and love her very much, and they argued a little bit over the dates. So if anybody out there is going to correct me, I'm sure I'm going to hear about it. She was one of the first women to attain that position of full tenured faculty. Her research focuses on coastal whole ecosystems, including using experimental mesocosms, examining nutrient, carbon, and benthic water column cycling. Candace uses her results to address the concerns of the people who work, live, and play in and along Narragansett Bay. Candace has been a leader in helping URI to determine how to manage Narragansett Bay, its resources, and all aspects of it, and keep it productive and sustainable for future generations. Candace has advised 12 master's and 13 doctoral students and served on 68 graduate committees to date. Although retired, she carries out an active research program focused on climate change in coastal systems and continues to work and advise on enforcing her commitment to train the next generation of students. Candace was president of the Coastal and Estuarine Research Foundation, or CERF, and has received wide recognition for her work, including the URI Scholarly Excellence Award, the Boswick H. Ketchum Award from Woods Hole Oceanographic Institution, the Lifetime Achievement Award from Save the Bay, and was inducted into the URI Lifetime Service Society. Thank you to her curious, hardworking, and collaborative nature, Candace is internationally known as an expert in coastal ecology and as a role model and mentor for many. I'm really pleased to introduce her today, Dr. Candace Oviatt, our 2020 recipient of the Distinguished Achievement Award.
Thank you, Paula. I appreciate that lovely introduction. And welcome to you all. Who would have guessed it would have happened to me, huh? And I know you'd all rather be up here than I would like to be up here. I'd like to extend a special thanks to all the technicians and intrepid students who gathered the data that will be talked about in this talk today. They've been going out on that dock in all weather for many, many years now. Also, I thank all the technicians and students that have responded to my endless requests for data. I appreciate your help. Today I'm going to, and I want to welcome all of you here. I see generations of Merle, and it's really taking me back a little bit. I'm going to talk today, I'm going to give you an update on the winter spring bloom. And I know I've done this in the past, and I thought it was appropriate I do this once more at least. This is a beautiful picture by Jan Rines of one of the boreal diatoms that's often dominant in the phytoplankton in the winter spring bloom period. Our winter spring bloom is not like the bloom of the North Atlantic. In that bloom, it takes time for the water column to become stratified. It's a little bit later in the year and warmer, and that bloom is consumed by zooplankton in the water column, which in turn support larval fish. And so larval fish year classes depend on the bloom in the North Atlantic. In our bloom, it occurs at the coldest time of the year, and it's over a 4 to 6 week period, just as the light begins to increase, usually in January and February. And it's cold, so the grazers are inactive, and it accumulates in the water column. And there's no grazers, and finally it just falls to the bottom as a pulse of fresh organic matter, which is then used by the benthos over the ensuing summer months. So the bloom in the North Atlantic is a pelagic bloom, and ours is a bloom which goes to the benthos at the coldest time of the year. First, a little history. When I arrived in 1961, the winter spring bloom was a big topic, and Dr. David Pratt was working on the annual cycle of phytoplankton abundance. Ted Smeda was working on the species of the phytoplankton and their life history with all his students, and finding out that what the limiting factors were in terms of light and nutrients. And John Martin was here working with David Pratt and looking at the grazing of copepods and their effect on the winter spring bloom. My first assistantship was on the fish trawl, and it gave me a lifetime interest in all the patterns of fish in the bay, primary production in the bay, and particularly the winter spring bloom in the bay. So after a few years, Scott Nixon joined the faculty here at GSO, and he was charged with developing a mathematical model of the ecology of the bay. So we went out and did a series of projects together trying to figure out the various components of the bay ecology, and we started with primary production. And we made our first primary production measurements between 1971 and 73 using dark and light oxygen bottles. We'd go out in 3 teams. It was a huge effort. 3 teams, East Passage, West Passage, and the Providence River. And we set out 3 or 4 profiles in each of those places in the bay, gather the bottles back after 4 hours or so of incubation, and come back to the lab where people would titrate them for hours and days afterwards. The second time we measured primary production was after the wastewater treatment upgrades about 25 years later in 1998. And this time we used a C14 method. We actually got the water from the same 3 locations in the bay, and then we incubated it in the Merle tanks, and then we related it back to the water column light distribution. Also a very tedious procedure that took a long time to do. Between those 2 blooms, there was a really nice winter spring bloom in the first measurement, and 25 years later, there was no bloom at all. So part of what I'm going to talk about today is what happened to the winter spring bloom, and what is it doing today, and what can we expect it to do in the future. So there's 2 reasons to study the winter spring bloom. First of all, it feeds the bottom fauna, and so their abundance depends on the amount of that pulse of organic matter early in the year. And the second thing is that the nitrogen and nutrient regeneration supports summer primary production to a much higher level than what you would get from ordinary runoff. So my student Greg Ellis did a study of 4 stations in the upper bay of bottom animals, And he found a direct relationship between the numbers of polychaetes in the bottom and also the number of all the juvenile and larval macrofauna, a statistically significant relationship between the pulse of organic matter, the strength of the winter spring bloom, and the abundance of benthic fauna. And we can't often see direct relationships between diatoms and macrofauna in field data. So this data on the right here is from one of the Merle experiments, a sediment, no sediment experiment, where we increased the nutrients in various treatments, with the final treatment being there. I think it's 4x with added silica. And you can see that the average daily potential diatoms are related very directly to the invertebrate biomass that developed in the bottom. So very direct relationship between the amount of phytoplankton, particularly the amount of phytoplankton in the winter spring bloom, and benthic animals in the bay, which in turn feed the fish in the bay. So the second reason that this is important is one of Scott Nixon's greatest contributions to coastal ecology was the nitrogen dynamics of that pulse of organic matter to the bottom and the resulting nutrient regeneration through the summertime period, which fuels the summertime primary production in the bay. The number I have in my head is it increases the summer phytoplankton production in the water column, particularly in the lower bay, by 40 to 60%. And that may have changed. I haven't looked at that number in years, but it's a big number and it's an important process. Of course, Scott also was one of the first people to define how important denitrification was to nitrogen dynamics. So here's our first measurement of primary production in 71 to 73. We measured a value of about 270 grams carbon per meter squared per year. It was a lot of work, and the data was pretty thin. You see, we only got out there about once a month that we could muster this kind of effort to get out there. But you can see there's a pretty good winter spring bloom here. Really nice in 2 of the years of our survey. And this is very typical of this period in the bay, the 70s, 60s and 70s. There's often and always a long winter spring bloom. And then in 1998, we measured primary production in the bay again using C14 dark and light bottles. I imagine it's almost illegal to use C14 these days, but we used tons of it and washed a lot of it down the drain as well. In this measurement, we measured about 320 grams carbon per meter squared per year. Which we thought with a change in methods in the time, it was probably not so different from the first measurement. But the really startling effect of this measurement was no winter spring bloom, not in the Providence River, not in the Upper Bay, not in the East Passage. In the West Passage, it is slightly elevated to the winter spring bloom period, maybe 7 micrograms of chlorophyll per liter, but really, really minimal, hardly any bloom at all in the bay. So the factor that I think was controlling that was the temperature. From the 1970s to the 1990s, the winter weather conditions had warmed by over 1 degree, in some cases 2 degrees centigrade. And so if we plot the mean temperature through the winter spring bloom period versus the bloom mean chlorophyll level, you can see that in very cold years, like 1977, 1996, we get a really nice winter spring bloom. And in 1998, when we measured primary production, or 1991, which was extremely warm, there's virtually no bloom at all. So temperature is a really important factor in determining whether it's a bloom or not. And the year that proves the rule is 1986. That's a fairly warm year, about 4.5 degrees centigrade, and yet we had a really nice bloom. And that's because in 1985 we had a brown tide bloom in the bay, or a coccus, which was a tiny little organism that nothing could eat, not copepods and not benthic filter feeders and not benthic infauna. So everybody failed to recruit that year. And so by the springtime, winter spring bloom time, there was no zooplankton in the bay and a really nice bloom. So to confirm that grazing was important, well, wait a minute, I got to continue on here. That to continue that cold temperature is important, I've pulled out this slide of more recent data. And in the middle panels here, we have East Greenwich Bay. Oops, sorry. We have East Greenwich Bay in, where did it go? East Greenwich Bay in 2017, and 2018. And in both years, as the temperature dropped, the red line here, the bloom starts to happen in December and reaches its maximum extent in January. Similarly, in 2018, as the temperature drops, it has to get below 3 or 3.5. We see that bloom take off, the winter spring bloom. And even with nutrient management that has reduced nutrients in the bay, East Greenwich is still very eutrophic. It's a very rich system, so plenty of nutrients there. So we still weren't quite satisfied that we'd shown that grazing indeed controlled the bloom. So Amy Keller, one of the people that was working with us, wonderful Amy, did this mesocosm experiment with ambient treatments, warm treatments, and warmer treatments. And she looked at what happened with the grazers during the winter spring bloom. So when the temperature was very low in the cool treatment, we got tons of zooplankton, or tons of chlorophyll, and no zooplankton. By contrast, in the warm treatment, we have tons of zooplankton and no chlorophyll. Pretty good evidence that it's the grazing activity which reduces the expression of the winter spring bloom in very warm years, as we had by the late 1990s. So another important factor is nutrients. And in the 1990s, phosphate was removed from detergents. And that meant that there was about 50% less phosphate coming into the bay. Phosphate is one of the potentially limiting nutrients in the bay. And from 2005 to 2012, there was a very huge effort to implement denitrification process into wastewater treatment plants so that the effluent was decreased in the nitrogen content. And they were hugely successful in this because it not only happened in plants that are on the bay, but also throughout the watershed. So there was over a 50% reduction in nitrogen coming into the bay. This is usually the limiting nutrient in the bay. So both limiting nutrients were decreased by about 50%, which means the ratio between the nutrients didn't change, and thus the species might not change. At least it wasn't a driving factor. So now there are some years since 2012 when the nutrients are so low that a winter spring bloom cannot be supported. And I'll show you some examples. And since 2005, we've begun to measure primary production continuously, every day of every year. And we're using the sensors on the buoys and fixed sites throughout the bay, 12 sites for the data I'm going to show you here today, measured every 15 minutes. And we've been measuring primary production since 2005 to the present. And so we're going to look at, and we also use pH. We like to do it by oxygen and carbon so we can compare the two ways of measuring. So here's the primary production measurement. I averaged the two values before our continuous measurements, the dark and light bottles, the C14 bottles, and it's about 300 grams carbon per meter squared per year. When the first nutrient reduction was implemented in 2005, there was a 30% reduction in nitrogen, so we see a big drop in primary production in the bay. And thereafter, it tends to wobble around about 200 grams carbon per meter squared per day. 200 grams carbon per meter squared per year. So the impact of a 50% reduction in nitrogen and phosphorus, not so limiting as nitrogen, but potentially limiting, has been a 1/3 reduction in primary production in the bay. And that's probably had impacts on our amount of winter-spring bloom production as well. So here's the nutrient story, one example at least. In 2018, we had a series of storms through the fall period and into the early winter, and lots of rain runoff and lots of nutrients going into the bay, despite the managed reduction of effluents coming into the bay. And we can see here that we had a very high dissolved inorganic nitrogen. And as that bloom started to take off in January, this was the biggest winter spring bloom in my career. In 2018, 35 micrograms of chlorophyll per liter. Amazing. I thought I would never see a winter spring bloom again after the 1990s, but here it is, all back, strong as ever. And in 2017, when there were no storms or runoff, dissolved inorganic nitrogen was very low through the winter spring bloom, and we only had a little minor bloom here of perhaps 10 micrograms per liter of chlorophyll. So nutrients also control the bloom expression. And this is an up-to-date picture of our relationship between temperature and bloom intensity. And here's our 2018 bloom, really nice bloom compared to 1977, 1996, and other high bloom years. And by contrast, here's 2015, also a very cool year, the coldest year in our record, -1 degree centigrade, and no bloom at all because there's no nutrients in the bay in that year. So temperature and nutrients, both very important to bloom expression. So what's happening now with the bloom? Why did it disappear from the 70s to the 90s? Why has it come back in the 2000s? And what is global warming doing to the bloom? This is not my work, but it's since it controls so much of our bay ecology, it's certainly an area where I'm deeply interested. And so bear with me as we go through this. And you probably expected me to talk about this today. So in the positive North Atlantic oscillation, we have a very zonal jet stream, which keeps cold air bottled up in the Arctic. And in our region, we experience very mild winters. And that was the case between the 1970s to the 1990s. And since the late 1990s and 2000s, we've switched to the more meridional circulation, wavy jet stream over the northern hemisphere, where very cold winds can come down over the continents in the northern hemisphere, and very warm winds go from the ocean north up into the Arctic. So in this case, we get very cold winters in contrast to the positive NAO, and during the negative NAO, we get very cold winters, or typically we get cold winters. And I'm going to try and explain why that's the case a little bit here. Here's the NAO distribution. You can see it increasing. It's the blue line here from the 1970s to the 1990s. The index gets higher and higher, and then abruptly falls in the late 1990s to more neutral conditions. And the thermal halide circulation exactly follows that NAO pattern. So it appears that there's a very good relationship between the thermal halide circulation, the North Atlantic oscillation, which is also the same as the Arctic oscillation. The topic of internal climate oscillations is still very controversial. There's still a lot of papers out there which don't like this. They think it's all external temperature oscillations. And there have been several recent papers claiming that factors like volcanoes and air pollution aerosols have controlled periodic reductions in temperature. And I was very surprised to see that Michael Mann, who is the tree ring person, a very famous scientist, he's gathered great amounts of tree ring data to look at the temperature oscillations going back several hundred years. And he believes now, based on his analysis of one of the climate model outputs and using a very sophisticated statistics, that those climate oscillations are due to external forces due to volcanoes in the past. And more recent changes have, he thinks, been due to probably sulfates from air pollution. And after the Clean Air Act, the CO2 increase in the atmosphere has contributed to warming. So here he is with these tree rings. Those are the patterns he revealed going back over to about 500, the year 500. And his paper concludes that there is no compelling evidence for internal multi-decadal oscillations in the climate system. So there's still a lot of controversy over what I'm telling you here today, but take it with a grain of salt, and we'll just carry on like he wasn't complaining about this work. This is a paper by Zhang. He's a proponent of the internal cycles. This is the Atlantic multi-decadal oscillation, and you can see that we have a warm North Atlantic period from the 30s to the 60s, a cooling period from the out into the 70s, and then a warming period to the current warm North Atlantic period. It's a very regular pattern. It's hard to believe that it's not governed by internal oscillations or regular oscillations of some sort. I should point out that currently we still have a warm North Atlantic, and it's perhaps going to last for another 5 or 10 years. So it shouldn't change very dramatically over that period of time. It could. And it's some question in my mind whether we'll ever see a positive NAO again, because I think the Arctic area will have to cool a good bit for that to happen. So there's, according to Zhang, there's strong observational and modeling evidence that the multi-decadal Atlantic meridional overturning circulation variability is a crucial driver of the observed Atlantic multi-decadal variability, and associated climate impacts, and an important source of enhanced decadal predictability. So they're beginning to think they can predict the decadal oscillation. So what happened locally to our temperature here in Narragansett Bay? So unlike the North Atlantic, we experience cold temperatures during a warm North Atlantic. So here in the 40s to the 60s, we have a cold Narragansett Bay. From the 70s to the 90s, we have a warming Narragansett Bay. And then since the late 90s and the early 2000s, we again have a cooling trend locally. And we can compare that with the strength of the winter-spring bloom. Here's the winter-spring bloom. This is each year since 1977. We've been gathering data off the dock. It started out as a control for our mesocosm studies, and it's gained in importance as the length of the record goes on and on. You can see there's only a few years when we have extraordinary high blooms, 77, 86, 96 was another one. 2010 was the year of the big flood locally, but prior to the flood, we'd already had a really good bloom in the bay. And then 2018, the most recent year of an extraordinary bloom. In most years, the bloom is between 10 or 15 micrograms of chlorophyll at the GSO dock. And this is data that has been gathered from the GSO dock. Oops, no, I don't want to skip that slide for sure. So this shows the pattern of chlorophyll in the bay. From the 1970s to the 1990s, chlorophyll decreases during the winter-spring bloom period. And from the early 2000s to present, it's been increasing. So decreasing 70s to 90s as the bay warms, increasing at least a little bit in the 2000s as the bay has chilled during the wintertime period. So why does the bay chill? And this is the expert. This is the person that predicts our winter weather throughout the Northern Hemisphere. This is Judah Cohen. He's at MIT. He's a meteorologist, and he's been focused on explaining why we get cold winters with global warming. He doesn't necessarily believe in the oscillation, but he does believe in Arctic warming and amplification of Arctic warming. The Arctic is warming at twice the global average rate of increase in temperature. And he believes that's due to the severe weather in our mid-northern latitudes. So he used both observations and models, and his observations show Arctic temperature amplification is linked to the extreme cold in the northern hemisphere. And his big example is last year, 2021. Do you remember that Texas, the electrical grid went out? They suffered $200 billion in damages as a consequence of that. Continuing, and other damages associated with the cold temperatures, and that was more than the damages associated with Hurricane Harvey. And then Cohen has also used numerical models. He's showing that there's forced trends between a lack of Arctic sea ice and Siberian snow cover. The Arctic, the open water in the Arctic puts a lot of water vapor into the atmosphere. Perhaps that is linked to increasing snow cover in Siberia. And his hypothesis is that it links to less ice in the Arctic and the more Eurasian snow to our severe winter weather. And the less sea ice and the more snow cover increases the probability of a high in Siberia, and that means there's a lot of repulsive energy which goes up into the atmosphere, and it's carried around by the atmospheric circulation over the Arctic, and because of that waviness in the jet stream, it comes down over the northern continents. Not just the United States, also Europe has been experiencing cold winters. So that increased wave energy flux of much higher pressures in the Arctic putting energy into the atmosphere results in severe winters in our more northern hemisphere locations. So here we have a picture on the left of a symmetrical circulation, very low pressure over the Arctic. And on the right, we see that this has stretched now so that the cold air is extending down over the northern continents. And this is the undisturbed polar vortex in January 2018 compared with the disturbed Arctic circulation in February 2018. This is from Cohen's 2021 paper. I want to bring your attention to the top two panels. In the top left-hand panel there, you can see low pressure symmetrical over the Arctic. The number of days from the 1970s to present has been decreasing when we have low pressure centered over the Arctic. By contrast, if we look at the other extreme, when we have high pressure in the Arctic, warm conditions in the Arctic, lots of energy going into the atmosphere, we have an increasing number of days of high pressure in the Arctic from over that same period of time, from the 1970s to the 2010, I think. So what is Arctic sea ice doing? I'm sure you think have heard that it's pretty much disappearing. In fact, the median concentration of ice in September, which is the time of the least ice in the Arctic, the minimum here over the seasonal cycle, this is 2012 when we had the least ice in the Arctic, and blue here is where we are today. This is September 2021. So still some ice in the Arctic, perhaps a slight increase from 2012, but nothing you would want to trust. The trend in ice over time, however, is very interesting. This is the area covered by ice over time, 1950s to present. The blue points are observations, and the red and black lines are from model output. And it's plotted in 10-year trends of sea ice extent. We see a minimum in 1997. That's actually data from 1997 to 2007. So total ice area has continued to decrease, but the rate of decrease is decreasing, and the trend is for ice extent to perhaps increase. So this is a paper by Jaeger. He says future forecasts from one of these decadal prediction models indicates that we should expect a pause in decadal Atlantic winter sea ice loss over the next 5 or 10 years. Let's see. So what does that mean for this winter and the next few winters? Here's the Arctic sea ice as of September 2021. It's less than the median line between 1980 and 2018, 2010, I guess. Anyway, it's less than what it has been over time. And you can see that if you were in a ship, you could easily go through the Arctic at this time in September when we have the minimum extent of ice in the Arctic. So lots of open water in the Arctic. And what about the Siberian snow? This is the blue indicates that there's a pretty good coverage of snow in Siberia, also northern Canada and Alaska. However, Dr. Cohen thinks this is a modest amount of snow, and he's very equivocal about the kind of winter we might expect coming up. So I can't give you a very solid prediction. Looks like we have a lot of open water in the Arctic. Looks like we have a lot of Siberian snow, but he's sort of expecting a mild winter because the snow extent is less than what might contribute to a very extreme winter here. So it's hard to know what the winter spring bloom will bring next 2022. We've had a lot of runoff through the summertime period, and into the fall that pattern of lots of rainfall has been continuing. So if that continues, we should have plenty of nutrients in the water column. So there's a possibility for a strong winter spring bloom coming up. But the main, very encouraging thing to me is that we continue to have very strong winter spring blooms, even in the face of global warming, because global warming or the phase of the oscillation is contributing to our very extreme cold winters here in recent years. So in summary, the winter spring bloom was prominent in the 60s to the 70s with cold winter temperatures. The winter spring bloom weakens by the 1990s with warm winter temperatures. Warm temperatures in winter support strong grazing by zooplankton and benthos, which controls the bloom expression. The winter spring bloom returns in the later 2000s with return of cold winters. Nutrient management has reduced the nitrogen input to the bay, so that there are several years now when we don't have enough nutrients in the bay to support a winter spring bloom. And cold winters in the northern hemisphere will continue with Arctic warming and with the negative North Atlantic oscillation. And we can expect that very warm winters may occur if the positive Arctic oscillation returns with the more zonal wind conditions. And during winters with high runoff, the winter spring bloom continues, at least so far. So thanks. Any questions? Peter.
So in our coastal environments, our blooms are linked to nutrient runoff or nutrient availability and hindered by zooplankton, primarily grazing. You contrast that with North Atlantic, which you gave us, where we have both low temperatures, I presume, even during.
They're actually warmer than Narragansett Bay in the wintertime to set up stratification.
Yeah, so it sets up stratification, but you do have reasonably large zooplankton herbivory on that zooplankton.
Absolutely.
In part, perhaps because there's a larger availability of nutrients that
Probably the expression of bloom, chlorophyll, and biomass is stronger here than what we get in the North Atlantic during the winter spring bloom. Those blooms are generally smaller than what we've seen in Narragansett Bay because the nutrient concentrations are not as large. But we're talking about vast areas supporting zooplankton, abundant zooplankton, and then subsequently larval fish. So there's kind of a scale change there, size-wise. Suzanne?
Candace, first of all, this was one of the favorite talks I've ever seen. I really wanted to thank you. Amazing. I did a little statistics by eyeball. It looks like there's a winter spring bloom about every 9 years, with the one exception of winter spring break. Do you think there's anything to that?
No, I think there's enormous variability in the winter spring bloom. The patterns of winters getting warmer through the 70s to the 90s, that was a very intermittent thing. Some years it would be 2 degrees warmer, and then it would be fairly cool. Weather is highly variable. So it's hard to pick out a long-term pattern unless you have decades of data, I think. And so, I'd love to see additional patterns and proof of additional patterns in the data, and I would look for it, but I don't expect it because of the high variability.
I just want to throw out the idea and get your input on, the winter spring bloom is a massive day-wide quote-unquote effort.
Yeah.
And I'm wondering if the day has to recuperate for a decade after.
Yeah. I don't think so because the nutrient input has been so constant. The wastewater effluent is, it neither storm nor hail nor whatever will stop the nutrients coming into the bay with the effluent. So it's still the dominant source of nutrients in the bay, even though it's been reduced by 50%. The cause of the extreme blooms throughout that record had variable reasons. Sometimes it's lack of grazing, sometimes it's excessive nutrients from storm runoff, sometimes it's very cold winters with nutrients combined. So it's very complicated and it changes every year. The huge advantage now is that we have the data so we can figure it out every year. We know what the bloom is doing because we have enough of the pieces of the puzzle. Way in the back.
Thank you for a great talk. I was wondering, on these years where you see a little bit warmer winters, that the bloom is dampened by zooplankton feeding, do you then also see smaller summer phytoplankton biomass with the idea that there's not as much nutrient regeneration that gets fuel in summer?
Yeah. Again, the amount of variability from one year to the next. We've not had a lot of luck tracing cause and effect. After a major input of organic matter, like the 2010 flood, we could see elevated productivity in the year after that, because I presume from the stored organic matter releasing nutrients into the next year, as well as the summer of that same year. And also in 2018, which we had that extreme bloom, it is the case that the next year, primary production did not drop as low as the average. It was still elevated relative to the average. So yeah, I think there's a carryover effect. I think in field data, it's really hard to detect. And I think mesocosm experiments would be the way to go to really dissect out cause and effects there. Yes, Jim.
I'm thinking this nutrient reduction is a really large perturbation.
Huge.
In the context of all of these oscillations and so forth. And I would expect that initially when you have those, that kind of an effect, it would be very large, but then the ecosystem would internally configure over time to try to find a way to be more efficient about nutrients and do more with less. Can you envision a mechanism that is happening or will happen?
Again, I think the variability in the events from one year to the next just confounds our efforts to tease that apart. Again, I think a mesocosm experiment where you try to look at that kind of mechanism would be more successful. and probably the way to go to figure that out. In our field data, I have to confess that we haven't recognized that kind of mechanism. Jim.
With respect to overall productivity of the bank, including economic productivity, fish productivity, and so on, as well as carbon collection, is there a good reason to continue to reduce nutrients into the bank? In a place like this, where it doesn't seem to be a problem with location.
At this point, it looks like the reduction of nutrients in the bay has been successful in reducing the periods and extent of time of low oxygen in the upper bay. It's taken several years of data to finally tease that out statistically, but it looks like it's significant now that hypoxia in the summertime in the upper bay has been reduced. I don't think it makes sense to reduce nutrients further. And we've been working on a paper where we say, really, couldn't we release nutrients in the wintertime, increase the nutrient input in the wintertime to let the winter spring bloom continue with not have years when there is no bloom because of no nutrients. So, yeah, I would argue that let's not reduce nutrients any further, and maybe we should change the seasonal pattern of nutrients with our managed nutrient abilities these days. Yeah. Way in the back.
This is an amazing data set. It's so interesting. Thank you. I was wondering, are there similar data and observations of winter spring blooms in other water bodies nearby?
Long Island Sound has a pretty good record. Mass Bay has a pretty good record. Chesapeake Bay has a pretty good record. Yeah, there's other long-term data sets. Maybe they're not quite as long as this, but yes, there are good records. Long Island Sound, yeah.
I guess the follow on to it, are there any, have you seen any similarities?
Yes, when there's been no bloom in the bay, temperatures have been warm in Mass Bay and in Long Island Sound, and there hasn't been a bloom in those two systems either. And there has been elevated zooplankton. There's enough field data so that you can see those same patterns. Yes, I would say. Yes, Tatiana.
Thanks for such an interesting talk. I want to follow up on Jim's question about nutrients. And that leads to your answer leads to the question of what do you think the bay looked like pre-anthropogenic? Where there was no what was that? What do you think that was?
Yeah, I think we could only guess. From what I know, there was a lot more biomass of higher trophic levels. Fish, lobster, were very abundant in colonial times. And I think, fishing has had a major impact on the bay ecology, which perhaps we haven't teased out very much. So a fairly low productivity over time, which is allowed to accumulate in long-lived higher trophic levels, I think contributed to that large biomass of what are now fishable species, which have largely disappeared from the bay.
Do you think that there was a muted spring bloom, a no spring bloom? I'm trying to sort of tease apart the.
I think there was a winter spring bloom. I think the mixing in the bay and runoff of winter storms brought nutrients into the bay, and that it contributed to a winter spring bloom. Not probably the intense and long duration bloom that we have become familiar with here. Yeah. Yes. Art.
If we go back a long time, there weren't any dams.
Right.
And so that means sediment borne nutrients as well as a massive amount of fish that used to occur. We had a whole watershed which was bringing its nutrients one way or another. What did that do?
Yeah, I can only speculate with you that brought a lot more nutrients into the bay on a seasonal basis to support such a bloom. So, yeah, good point, Art. Jim.
I remember Scott Nixon's horse craft talk.
Yeah.
Where there was a huge nutrient loss due to all the horses that were. I don't
Right.
remember what he had to say about the bloom.
Yeah, the runoff from the urban areas of horse manure, yes. Yes.
I was wondering if you could speak a little bit more to the role of precipitation with blooms. Like, is there a relationship between, say, annual precipitation and the magnitude of bloom, and how you might expect local precipitation to change in the future?
Yeah, I don't know. We looked at the pattern of storms from time to time, and it's pretty variable. It looked like rainfall was increasing in the 70s to the 90s. It looks like it might have been decreasing a little bit recently, but then in this year we've had a good rainfall. Very sporadic years when we get good rainfall. 2006, 2009, 2013, 2018. So I don't know. I don't know what the pattern is in rainfall. The reason rainfall brings in nutrients, though, is again an anthropogenic one. It's taking nutrients from septic systems and even old septic systems that are no longer in use, and that runoff is bringing. It's still sewage nutrients coming into the bay. Yeah. Lucy.
Yes, yeah, this situation in the North Georgia, with the winter spring blooms, has this been a change in the relative proportion of the usual flavor in terms of, I mean, this is kind of taxonomy. I was just wondering.
My strengths. Taxonomy is my strengths.
I was just wondering whether you know.
Yeah. I think you probably know more about that than I do. I know the boreal diatoms, their abundance decreased in the bloom patterns through that warming period. I know that in some of the recent blooms, Jan Rhines, these are recent pictures from Jan Rhines, that some of those species have returned when we have really cold winters. So overall, I know skeletonema was perhaps the most abundant, both in winter months. I'm sorry, Tatiana, I know that's several species now. The skeletonema is dominant both winter and summer and some of the warmer periods of the winter spring bloom. So yeah, I'm not the person to talk about with taxonomy, but it does, I think, change with warming conditions, but it can revert, I think, when we get colder conditions again. Yeah. Okay, I wore you out. Thank you all.
Thank you so much, Candace. I would like to invite everybody outside onto the quad now. We are going to do a short ceremony to dedicate a commemorative bench for Candace and all of her work. So please join us, and thank you again, Candace, for a wonderful talk.